Well, greetings and welcome, everyone. Thank you for joining us here today at this year's 2022 HPCC Systems Technology Summit and Conference with the theme of making a difference and changing the game, where that is exactly what we have done once again. We have been and continue to make a difference and make significant improvements to our HPCC Systems platform and change the game. I'm very glad that you chose to join us here today, as this has been an eventful year and a very exciting time for us. And I'm equally excited to tell you a little bit more about some of these recent developments. A little bit about myself. My name is Greg Panagiotatos. I'm a senior software engineer on the HPCC Systems platform development team. I'm based out of our Boca Raton office here in sunny Florida. And for this presentation, I'm presenting material on behalf of our team, and specifically Gavin Halliday, whom we all know is one of the main architects of the HPCC Systems platform. Gavin is based over in England, indicative of how our HPCC Systems is truly a global platform, which leads me to ask each of you a favor. Since our conference is virtual, the idea you could be joining from anywhere in the world listening to me right now is quite fascinating. Now, if you wouldn't mind taking a second and just putting down in the chat where you're joining us from today, I'd really like to know where you're all joining us from and consequentially generate some fairly interesting data that some of the folks around here might even be interested in having a go at, maybe generating a graph or visualization or such. At any rate, I'd appreciate that. So our presentation today is going to have a look at the improvements that we've made to the HPCC Systems platform working with Git repositories. And we're going to be looking at the Git improvements, what they are, speed improvements, compiling directly from Git, using multiple repositories. We're going to have an example and how to migrate from a single repository to a multiple repository model. We're going to show how you can compile directly from Git, like we said, using branches, tags, or commits. We're going to look at packages and how we handle dependency resolutions, local development options, command line options, advanced options, configuration options, and authentication and security options, all in the next 45 minutes. So, as many of you know, we recently celebrated our 10th year of being an open source platform. And for many of those years, HPCC Systems has had support for the server, the ECLCC server, to compile ECL code from Git repositories. The repositories and the optional branches are configured using environment variables on the server. Using this Githook mechanism, you can submit a query from a branch, and the ECLCC server will pull the source from a GitHub or GitLab repository and compile it. This allows you to deploy a specific version of a query to production without needing to perform any additional work on the client side. Let's look at some of these improvements. The speed. The code for interfacing with Git repositories has been significantly and noticeably improved. On large queries, this can reduce the compile time by literally tens of minutes, which, for those of you dealing with SLAs, can be very significant. We use a library now to read the repositories directly. We've added support for resources and manifests from Git. Previously, manifests and resources were only associated with a query if they were contained in source files, which meant they weren't included when compiling using the Githook mechanism. And again, the game has changed. We've added support for GitLFs. GitLFs is an extension to Git that improves support for large files and is supported by GitHub and GitLab. This is particularly useful for large resources. For example, Java packages, which are included as part of the manifest. Recent improvements to the platform have significantly improved the support for compiling from Git repositories. And some of these improvements have been backported to the older support releases, such as 7.12. Now, in order to update to the latest point release, in order to get all these recent improvements. But the speed improvements alone are a compelling enough reason to ensure that you are up to date. With the Githook mechanism works well when all the source is contained in a single repository. But this doesn't scale so well for large projects. and there are very likely large project teams with multiple users. For example, you might have one team providing a common utility code shared between many teams, another team responsible for data ingest or index generation, and another third team creating queries using that data. There are likely other teams developing external tools such as Salt or Cal, or even bundles. So how would you manage these independent source streams? Well, previous to the Git improvements, you had two options. Single repository, where all teams work on a single repository, teams working on different products with different schedules needed to maintain separate sets of branches for different versions of the code, all within the same repository. Changes needed to be merged between branches owned by the different teams. Managing these multiple semi-independent branches in the same repository is probably a recipe for confusion. The other option is merging repositories, where each team works on their own repository and merges changes in from other repositories as needed. The advantage here is that the branch structure within the repository is simpler, yet integrating changes from other teams is probably much trickier. How would you ensure all the changes from the other team are taken? How do you avoid problems with incompatible changes or dependencies? Most likely, this would lead to multiple copies of the same source not really being kept in sync. So this is the problem that our recently improved Git support aims to solve. Now, starting with version 8.4, we've included all these Git improvements integrated into the HPCC Systems platform code. As we mentioned, some of the features have been backported to 7.12, the more recent point releases. And best of all, you don't need to install anything separately. No plugins or add-ons. You just install the platform and you get it. Now, like we said, we've significantly improved the support for compiling directly from Git. By configuring this Githook mechanism, you can submit a query from a branch, and the ECL/CC server will pull the source from a GitHub or GitLab repository and compile it. This allows you to deploy a specific version of a query to production without needing to perform any additional work on the client side. We've extended this --main option syntax to compile directly from the Git repository. Using this command here, compiling the ECL run command in the following format with the --main option, specifying the version 1 branch of the ECL demo D repository. This submits a query to Thor via ESP. It retrieves the ECL code from the version 1 branch of the demo D repository, compiles the code in the demo.main ECL file, and runs that query on Thor. The checkout is done on the remote eclccserver server rather than on the client machine. So the reference to the repository location uses the following syntax: protocol, the URN, the username, the repository, and that hash version. And we're going to look at the hash version in a little bit more detail in just a bit. Note, if the protocol and the URN are omitted, then a default will be used. This allows you to run a simplified version of the ECL command using the --main option, as illustrated in the second example on this slide, without the need to include the protocol or the URN. Now, the version text that follows the hash mark can take one of the following forms. It could be the name of a branch, be the name of a tag, or the SHA, the secure hash algorithm of the commit, or as I like to refer to it, the commit. Something to keep in mind, though the secure hash algorithm itself is a rather long, nasty string, you only need to refer to the first 6 characters. So let's have a closer look at some of these values. The first command on this slide references the code stored in the commit by its SHA. The command would always compile the same code that's stored in the specific commit referenced by the first 6 characters of its secure hash algorithm. The 3C2CA commit. Like I say, I call it the commit. Well, the second command example would compile whatever's in the version 1 branch. Now, if that branch happened to change, if it were updated, then the updated code contained in the branch version 1 would be what got compiled. Now, also note that this feature is supported for local compiles using the ECLCC. You can also use the -syntax option, as illustrated here in these examples, to check the code's syntax. And as we frequently state in our documentation, it is always a good idea to check the syntax. In the first example here, you check the syntax for the 3C23CA, the commit. And the second example would check what was in the version 1 branch. And since we've already demonstrated how the code in the branch can get updated and possibly change, it makes even more good sense to always check the syntax. Packages. There can be a problem when merging source code from multiple teams. You could have clashes. Clashes could occur if the teams have modules with the same name, or other errors as well if you're using the legacy import semantics. So these are the issues that we've addressed in version 8.6. Queries can now be compiled from multiple repositories, avoiding problems with clashing symbols. This ensures that the dependencies between the repositories are versioned. With these Git improvements, you no longer need to worry about these types of clashes. The latest HPCC Systems platform improvements allow each Git repository to be treated as a separate, independent package. Dependencies between the repositories are specified in a package file, which is checked into the repository and versioned along with the ECL code. The package file indicates what the dependencies are and which versions should be used. So many of these ideas are the same as those used by the Node Package Manager, or the NPM. So let's take a closer look. Consider this package.json file. The package file here gives a name to the package and defines its dependencies. The dependencies property is a list of key value pairs. The key, in this case, the demo repo D, provides the name of the ECL module that is used to access the external repository. The value is a repository reference, which uses the same format as a repository using the --main syntax as we just saw before in the previous slide, as well as that hash text value, here using the version 1 branch. To use definitions from the external repository, you need to add an import definition to your ECL code. For example, consider this ECL file on this slide. The name demo repo D in the second import statement matches the key value from that package.json file. This code uses a format mask password attribute from the repository ghaliday gch ecl demo d, which was the value assigned to the demo d repository. Each package is processed independently of any others. The only connection is through explicit imports of the external packages. This means that packages can have modules or attributes with the same name, and they will no longer clash with each other. Here's a couple of examples using multiple packages. The first one here is using package.json file. You can see the dependencies here listed under the dependencies label using the v1, v2 demo repo D repositories. The second example is using query ECL to import the repositories. You can see where it's using the version 1 v1 and the version 2 v2 branches from the demo D repository. Using multiple repositories like this can be useful if different teams have dependencies on different versions of a third-party repository, such as GitLab or GitHub. It's possible to use code from both teams without having to resolve the dependencies first. We've added local development aids. Options have been added to both ECL and the ECLCC commands to aid ECL developers where the developer is working on multiple repositories at the same time. The -R option indicates that instead of using source from an external repository, the compiler should use it from a local directory. The hash version text supports the same syntax previously demonstrated using the -main or the dash syntax or in the JSON examples from before. So this command, the ECL run examples -R option, will use the ECL code from the demo repo D from the user's home directory, rather than the code in the version 1 branch, as the second example on this slide shows. Now, it may be helpful to add the -V option or the -V option to enable verbose logging output, including details of the Git requests, particularly for debugging. Advanced options. These are Git values that can be passed in by use of the Helm charts for cloud configurations. The eclccserver server Git username is used to provide the Git username. On the cloud, the eclccserver server instances are ephemeral, but the same repositories can be shared by queries to be able to cache and share cloned packages between instances. So then we would define this secrets.get value. And we'll have a closer look at secrets when we get to the authentication section. The ECLCC server get plane option allows the user to define a storage plane that external packages are cloned to. Since the ECLCC server instances are ephemeral, if the repositories were cloned to local disks, they would need to be cloned for every query. By storing the repositories on a persistent plane, the downloads can be shared by multiple repositories, and the system only needs to download the updates. If this option were not supplied, the default would be the first storage plane with the category of Git. Otherwise, the ECLCC server uses the first storage plane with the category of DLL. We've added options for the ECL and the ECLCC. The default Git prefix option changes the default prefix that is added to relative package references. The default can also be configured using the environment variable ECLCC default Git prefix, as shown here. Otherwise, it defaults to https github.com. Fetch repos. Setting this option tells whether external repositories that have not been cloned locally should get fetched. This defaults to true in 8.6. It may be useful to set this option to false if all external repositories are mapped to local directories to double check if they're being redirected correctly. And the update repos option updates external repositories that have been previously fetched locally. This option defaults to true, but it's useful to set this option to false if you're working in a situation with no access to external repositories, or to avoid overhead of checking for changes if you know there aren't any. The ECLCC repository path, this value sets a directory that the external repositories are cloned to. So on a client machine, this defaults to the directory shown on this slide. Likewise, the corresponding directory on the Windows machines. In order to force a clean download of all the repositories, you can delete the contents of this directory. The Node Package Manager. For most developers, the package JSON files referring to dependencies should be sufficient. But it's possible to use the Node Package Manager to ensure that labels or branches are tied down to specific commits or their SHA. For example, this command here creates a package lock JSON file in the same location as the package JSON file. The Node Package Manager program will resolve the references to branches and resolve them to the corresponding SHAs. The package lock only option indicates that the Node Package Manager should not clone any associated versions of the code to the node module directories. Let's have a look at an example. The generated package lock JSON file will contain code similar to that depicted on this slide, where if a package lock JSON file is present, it will take precedence over the package JSON file. And the ECL is compiled in the same way, with the eclccserver server automatically downloading the dependencies. So what's the advantage of using package lock JSON over the package JSON file? Well, it allows you to use the Node Package Manager's semantic versioning, which is not currently supported by the eclccserver server. It also allows you to use a branch in your package JSON file as a logical dependency, but resolves it to an actual dependency on a specific commit, or rather its SHA, so that if the branch does get updated, the query will not change. The Node Package Manager install can also be used without the package lock only option. And this will check out the appropriate version of the code into the node modules subdirectory of the current project. ECLCC supports the node module structure as a way of providing the source for external packages. This is an alternative way to compile the code using ECLCC completely independently from the source control system. And now we'll look at migrating. If you had an existing single repository and you wanted to split it up into multiple repositories, what would be the best way to go about doing that? Well, this is best illustrated using an example. Let's look at extracting the common utilities currently in a UT module into a separate repository. The original ECL code that uses it might look like this, as illustrated here. Note the import UT statement. The aim here is to extract all of the UT module into another repository and modify the example code to use it. So first, we'll define a package file indicating your example code is now dependent on a new external repository, as illustrated here. Then you move all the utility code into this myorg shared utilities repository. And then you check it in as the version 1 branch. And then you can delete the utility code from the original location. And change the remaining code to use that imported external package, as depicted here, with the import utilities.ut or the import utilities in the second example. Now, if you're starting from scratch, this would be the cleanest way to express these imports. However, it can be painful to have to go through all the existing source, replacing import ut with import utilities.ut. So an alternative is to define an attribute in the example repository, which defines an alias for the module from an external repository. In this case, that means creating a ut.ecl file within the root of the main repository, as illustrated here. With this definition, all existing imports of UT will continue to work and will now refer to the code in the external repository. Your existing source can remain the same. One consequence of using this approach is that it prevents you from having modules with the same name in different repositories. So probably a best practice might be to provide unique names for your modules. Let's have a look at macros. Macros differ from other ECL attribute definitions because they're expanded as source in the context where they're called from. This means any identifiers are interpreted in the calling context instead of the context the macro is defined in. This can cause problems for imports within macros. Now, consider the following. If you had this attribute for processing all fields in this UT processing process file ECL file, such as this, if this macro is then moved into a separate repository, when it is next called, the import UT will be processed in the context of the caller's repository. Now, that would work if the calling repository contains an alias for UT, but otherwise, the import would fail. To ensure that the correct definition of UT is used, you can use the $$ symbol in the macro. This symbol expands to the module or folder that contains the definition of the macro, in this case, the UT processing, including the context of the repository in which it is defined. The example definition will work from wherever it is called, where this $$ corresponds to UT processing, so that $$ corresponds to UT. Bundles. Some of these features overlap with the idea of ECL bundles, which are packages of ECL code that can be installed and used from your own ECL code. The key differences are that imports within bundles need to be relative. Bundles need to be installed before they can be used. And there's no way to create a dependency on a particular version of a bundle. It just depends on what's installed. Now, the new Git package mechanism can be used to include existing bundles. So instead of installing a bundle, using the first command on this slide, the ECL bundle install command, you would instead use the second form, the package.json file, to do the install for you. The advantage of this approach is that there's a clear dependency on the version, and the bundle does not need to be separately installed on the eclccserver server machine. So one minor implication of this new feature is that the archive format's been extended. Each external package will be included as a nested archive with a package tag to indicate which package it corresponds to. All external archives are contained within the root archive, and external packages will only be included once. Authentication. If the external repositories are public, like ECL bundles, then there are no further requirements. Private repositories, however, have the additional complication of requiring authentication information, either on the client or on the ECLCC server side, depending where the source is gathered. Git provides various methods for providing these credentials. The recommended approaches for configuring credentials on a local development system that's interacting with GitHub is to use an SSH key. In this scenario, the SSH key is associated with the local developer's machine, is registered with the GitHub account. This is used when the GitHub reference is in the form of SSH:/ like github.com. The SSH key can be protected with a passcode, and there are various options to avoid having to enter the passcode each time. For more information, see the URL here for the GitHub docs page, the About SSH doc. The second approach here uses GitHub authentication. you need to download the GitHub command line toolkit, and then you can use it to authenticate all Git access with a single command illustrated here, the ghauth login. This is probably the simplest option if you're using GitHub. And more details about using this can be found at the documentation page listed, the cli.github.com auth login page. And you could use a personal access token. These are similar to a password, but with additional restrictions on their lifetime and the resources that can be accessed. They can then be used with various Git credential caching options. An example can be found here at the URL provided on the slide, the git-scm Git tools storage page. It is preferable to use the HTTPS protocol instead of the SSH protocol for links in the package lock JSON files. If the SSH protocol is used, it requires any machine that processes the dependency to have access to a registered SSH key. So all of these authentication options are likely to involve some user interaction, such as passphrases for SSH keys, web interactions with GitHub authentication, and initial entry for cached access tokens. This is problematic for the ECLCC server, which cannot support user interaction, and it is preferable not to be passing credentials around, as we should always be keeping a security mindset. The solution here is to use a personal access token securely stored as a secret. This token would ideally be associated with a special service account, and using the secret avoids the need to have to pass credentials around and allows the keys to be rotated. The following slides describe secret support in the Kubernetes and bare metal versions of the HPCC Systems platform. To use Kubernetes, add the Git username property to the ECLCC server component in your customization YAML file, using the key value pair illustrated here. To add a secret to the customization YAML file with the key that matches the username, as in this example, the second example on this slide. Then you'd add a secret to Kubernetes containing the personal access token, as illustrated here. And then you'd apply that secret using the kube control apply command, where the query is submitted to the ECLCC server. Any Git repositories are accessed using the configured username and password from the previous steps. And then you store the secret in a vault. You can also store the personal access token inside a vault. See the documentation and the values YAML file for more details how you'd configure vaults. Bare metal systems require similar configuration steps. You would define an environment variable, HPCC Git username, and then you'd add that Git username property to the ECLCC server process entry in the environment XML file, as an example illustrated here on this slide. Then you'd push it out to all the nodes, and you would need to do one of the following two options. You could store the access token in a secrets directory, as shown here, for example, illustrated using the cat command, or you can store this credentials in a vault. Within the environment software section, you can now define a vault section. For example, as illustrated here. The above entries have the same content as the entries in the Kubernetes values YAML file. The XML in the previous slide corresponds to the YAML illustrated here on this slide. And this about wraps up my presentation for this afternoon. We covered quite a lot of ground. We've looked at the improvements, compiling from Git, multiple repositories. Like I said, quite a lot of ground. Hopefully you were able to ask questions in the chat, as well as letting us know where you were watching us from, remember. However, I'd still like to open up the floor to any questions at this time. And should we run out of time, here's our contact information. Once again, my name's Greg Panagiotatos, and on behalf of Gavin, myself, and the whole HPCC Systems platform development team, I want to thank you for attending today and listening to my presentation. I sincerely hope you found it helpful and game-changing. Until next time, we'll see you in the clouds.